So we're in section 13.4. Someone posted a comment on one of my videos yesterday. Said, "Thanks, dude." All right. So, if we can remember, way back in Calculus 1, we said for a function of a single variable, so we have y equals some function of x. We define the differential of y is, we said dy is f prime of x dx. And we could use differentials as a way to approximate a function with a linear function. That was the point of doing differentials. So we kind of linearize the function. We're going to do something similar with multivariable function. We're going to extend the concept to multivariable functions. This idea of differentials, this idea of approximating our surface with, essentially we're approximating our surface with a plane. And we're looking at how the plane changes rather than how the function changes. Just as a way to, we might need to simplify our work, our function might be really complicated. We might need to maybe write a computer program that works with this, and it's easier to use a linear function in the computer program to get the information out that we want. So those are some of the reasons why we might want to use this approximation. So we're going to call a small change delta x and delta y. So our variables are changing. We have a multivariable function. We're going to call delta x and delta y the increments. Of x and y. So just these small changes. And then we're going to use these increments of x and y to find the increment of z. The small change in z. So we have z is a function of x and y, multivariable function. The increment of z is delta z equals our function at x plus delta x, y plus delta y, minus f of xy. So we're just evaluating our function at some point, and we subtract the value of the function at the point that we started. So we're just like we would expect. So we're going to call this the increment of z. And we draw a quick picture of what we're talking about here. Here's my coordinate system. And we're going to look at this point at y. So we're going to say, redraw that, go. This is y, and we're going to move over a certain distance, delta y, and we're going to go from x, and we're going to move over a certain distance, delta x, and I'm going to project those across like so. So there's our x and y, and x plus delta x and y plus delta y. And we have our surface up here above the plane. So there's our generic picture of a surface. And we're projecting these points, I'll do that in red, up to the surface, like so, and up to the surface like so here. And then this distance between the 2 points as we project it over onto the z-axis is delta z. So all this expression tells us is how the function changes as we move from x to, we move over a certain distance, delta x, and on the y-axis we move over a certain distance, delta y. How does a function change as we make that change in x and y? So using this idea, we're going to define the differential. This is our starting point here. We're going to define the differential. What we're trying to do is get a way to get this approximation for delta z without having to evaluate the function at the different points. So we want an approximation. So we're going to define our differential, dz, we're going to define the differential as the change in height of the tangent plane. So we're defining our differential change in height of the tangent plane to f from our 2 points, from xy to x plus delta x, y plus delta y. So rather than looking at the function, we're going to look at the tangent plane and see how the height of the tangent plane changes. Because a tangent plane is a linear, the equation of the tangent plane is a linear function of x, y, and z, rather than some other more complicated function. We're not going to go through the argument to show that this is the case. We can show, the kind of famous last words in math, we can show that dz equals dz dx delta x plus dz dy delta y. And we usually write, you usually see it written rather than as delta x and delta y, you'll usually see dz rather than delta x and delta y, we write a dx and a dy. And we call this the total differential of z.
Mr. Green,
Yes.
doesn't that statement say dz equals 2dt? It's not a...
Which one?
Oh, okay, never mind. Never mind. Yeah, they're Bilities.
I'm confused now.
You forgot the curly things.
Oh, okay. Yeah, Liam.
Should we call them del or del?
Well, we're going to have another symbol that we call del.
I'm going to call them del. Del is the
Upside down triangle, right. Yes.
Wikipedia says you can call those dels.
Or you should just call them duh. If it's like not a full D, just call them duh. For example, dz equals the z to x, d to y.
Why don't we just call them
It's way too complicated.
I like that, I like that.
We should just call them Q.
Call them Q.
Yeah.
Yeah, just call them like arbitrary.
QZ, QS.
Or just call it a partial.
I mean, we won't.
Right, we could call it the partial of z. So dz is the partial of z with respect to x times dx, plus a partial with respect to y times dy. So we call this the total differential. So this is the total differential of f of xy, of z equals f of xy. Couple of important things. When we write this as with the dx and the dy, in this particular case, we're not implying that dx and dy are infinitesimals. They're not infinitely small. We're just using dx rather than delta x. So the dx and the dy are still representing increments. So they're representing small changes, but not necessarily infinitesimal changes. At a particular point, x and y, the partial with respect to x and the partial with respect to y is just a number. So this total differential is a linear function of delta x and delta y. So this is a linear approximation to the increment delta z at a particular point. So the total differential gives us a linear approximation to the change in the surface at a particular point. And as delta x and delta y, as the increments approach 0, we get a better and better approximation to delta z. So we can say as delta x and delta y approach 0, our dz more and more closely approximates the increment. So I'm going to say as delta x and delta y approach 0, dz is approximately equal to delta z. So this our total differential is a better and better approximation to the change in the height of the surface. And we can write, so we're just going to equate our expressions for these two. F of x plus delta x, comma y plus delta y, minus f of xy is approximately equal to our total differential. And our function evaluated at x plus delta x and x plus delta y, I'm just going to rearrange. Is our function plus the total differential.
Is it over
df dy, sorry. And this is exactly like exactly the way we use differentials in single variable calculus, where we said f of x plus delta x is f of x plus f prime of x dx. So exactly the same idea. And the main application of differentials is to approximate a function. Rather than using the function itself, we use a differential as an approximation. The differential gives us a linear approximation to the change in the function. Questions on the exposition about what the total differential is. All right, let's look at a couple of examples, and then the total differentials do lead to an interesting idea about multivariable functions. So I'll show you how we usually apply them, and then I'll talk about the more interesting idea. All right, so for this particular example, we want to find z equals f of xy. We don't know the function. And we want to use the total differential to approximate this quantity. 2.03 squared times 1 plus 8.9 cubed minus 2 squared times 1 plus 9 cubed. So we want to find some function that would model this, and we're going to approximate this with a total differential. Well, we know that our delta z, our change in our function, is f of x plus delta x, comma y plus delta y, minus f of xy. So we're going to compare the forms of these two. We're going to compare the form of this expression that we have, and we're going to compare this expression for delta z, and come up with an expression for our function. So looking at these two forms, what would you say if I were to write f of xy? What would be a reasonable expression without variables, just with our numbers plugged in? What would be a reasonable expression for my function? Anybody have an idea? One plus, so the parentheses suggest we have something like 1 plus y cubed, and out front x squared. So this is x plus delta x and y plus delta y minus f of x times, or minus our f of x, f of xy here. Because and then using this, what we have is delta x would be what here? 0.03. So delta x equals 0.03, and x equals 2. And delta y would be negative 0.1, and y would be 9. So now we've come up with our expression for our function, and we're going to use a differential to approximate this rather than calculating it this way. We could calculate it this way, not a difficult calculation, but we just want to use a total differential to approximate. So our partial, we need our partial with respect to x. df dx of our function that we found is going to be what? For this function? 2x times 1 plus y cubed. df dy, our partial.
Is the cubed inside or outside?
Oh, sorry, thank you. df dy is going to be
3x squared 1 plus y to the second.
3x squared times 1 plus y to the second. Get my exponent in the right place this time. And at the 0.29, our differential is 4 times 10 cubed times 0.03. This is delta x, and plus 3 times 2 squared times 10 squared times negative 0.1. My differential, df, is the partial with respect to x times delta x plus the partial with respect to y times delta y. So delta y is negative 0.1, and I'm just plugging in my x's and y's into my partial derivatives. Okay? And then we can calculate this out, and we say that what we come up with is that df is, for this problem, it comes out to 120 minus 120 equals 0.
How does that make it easier to solve now?
On this particular problem, it doesn't necessarily make it easier. This is just an example of how we would do it. We'll do another example that's kind of a little more along the lines of how you might apply a differential. So this was just an example looking at the form of our expression, figuring out what multivariable function might represent that expression, and then using the total differential to do this. But yeah, this calculation not necessarily easier than that calculation. All right, questions on the process? Okay. So this would be more along the lines of how you might actually apply a total differential. So we have a right circular cylinder. Our radius and our height are measured with possible errors of 4% and 2%. We want to approximate the error in measuring the volume. So we have a right circular cylinder made out of some kind of material. We measure our instruments, measure our radius and our height with these possible errors. If we calculate the volume, we want to know what the approximate error in our volume is going to be. So the volume, the error in our volume, we're going to use a total differential, is the partial of E with respect to R times dr plus the partial with respect to H times dH. Now when we have a measurement error, what is this? When we say we have a measure a quantity with a possible error of 4%, how do we represent a measurement error? 4% is not dr.
Plus or minus whatever 4% of
Delta R and delta H.
So these are related to delta R and delta H. When we talk about a measurement error, our measurement error is actually the change over the original. So dr over R is 0.04, and dH over H is 0.02. So when we have a measurement error where the 4% comes from the change over the original. So dr over r is 0.04, dh over h is 0.02. That's how we. Yeah, so we say that our measurement error for r is 4%, measurement error for h is 2%. Right. Could have been more clear on that. So when we have a measurement error, it's the change over the original. That's what a measurement error is.
Alright, you just swap out the dr with 0.04r.
So we need an expression for our volume. What's the volume of a right circular cylinder? Pi r squared h. The area of the base times the height. So our differential, dv dr, we need our partial with respect to r, is going to be what? 2 pi rh. And the partial with respect to the height is just pi r squared. Our differential, our total differential, is going to be 2 pi r h times dr plus pi r squared dh. And our error, our measurement error, is the change over the original. So dv over v, our error, is 2 pi rh dr over our original volume, pi r squared h, plus pi r squared dh over our volume, pi r squared h. And when I simplify this, what do I get? The pi's cancel, I get an r on the bottom, h cancel, so I get 2r, or 2 dr over r, plus dh over h. So this works out nicely. So our error is going to be 2 times dr over r is 0.04 plus dh over h, which was 0.02, which is 0.1, or about 10%. So if we measure our radius and volume with the error of 4% or radius and height with an error of 4% and 2%, our error in our volume measurement is going to be approximately 10%. So this would be one way that you would apply differentials to come up with these error approximations. Questions? All right. So the interesting extension of differentials comes into play when we talk about differentiability. Now I said the other day that we defined the partial derivative, and I said that if the partial derivative exists, we say that the function is differentiable. That is not totally accurate. We can have, with functions of several variables, we can have functions where the function is where the derivative can exist where the function is not continuous. So we can have a function where the derivative exists, but the function isn't continuous. So the existence of the derivative doesn't necessarily is not going to be a good definition of differentiability. What we do is we use differentials to define differentiability. So we say that if this differential exists in a particular form, that defines the differentiability of a multivariable function. If functions are well behaved, then if the derivative exists, the function is differentiable. But we can have certain kinds of functions where a derivative exists where the function is not continuous, and that doesn't match up with what we knew about functions with single variables, because for a single variable function, if it wasn't continuous, the derivative didn't exist. But for a multivariable function, we can have the derivative exist where the function is not continuous. And that comes from the idea, we use the differential to define differentiability. If you're interested at all in that idea, page 917 through 920 of your book has some information on differentiability. All right. Homework. I think you'll like this one. There you go.